Okay, in this video, I'm going to cover part of section 9.6. So at the top of 9.6, this is on page 23 of your guided notes book. It says trigonometric ratios and using trig in applications. I'm going to hold off on the applications part. This video will just cover the trigonometric ratios here on the front of this note page. So first of all, using trigonometric relationships right here. Assume theta. This right here is the Greek letter theta. I don't know how many of you are familiar with this Greek letter. But again, it just represents a variable. Like we use x a lot for solving in equations. Theta is just as common in geometry. So theta is like the most common used variable, so to speak, for angle measures. At least the most common one that I've seen and used. So we just kind of let theta equal one of the angles when we're trying to label in a triangle so that we know which one we're talking about. If I'm going to make a triangle and one of them, oh, that's a triangle, yikes. And one of the angles is labeled theta, then I know kind of which one I'm trying to find when it says find theta. If given one of the trig ratios, we can find all of the other trig ratios using these steps. So there's kind of two ways you can do it. Step one, you can draw a diagram of the right triangle and use the trig ratio it gives you to actually put together those two lengths that create the ratio. And then use that Pythagorean theorem to find the third side. And that's the one I'm going to show you first of all. You can also use this trigonometric identity that is always true. And I'll talk to my honors classes later a little bit about what this trig identity means or where it comes from. For my non-honor student, I would just stick to these first three steps. So I'm going to go through example 1 using those, and I'll do a few other examples using those steps. And then my honor students, you can hang on until the end of the video and I'll just talk to you quickly about the identity. So first of all, when it gives you a trig ratio, so for example, this one says, find the cosine of theta given that the tangent of theta is 24/7. So remember, trigonometric equations are composed of three things. They're composed of an angle and a side and a side. So if I look at tangent, now remember SOHCAHTOA, again I'm going to write it over here because we just use it all the time. So SOHCAHTOA. Tangent relates two sides, the opposite and adjacent. So if this represents, right, the opposite and this represents the adjacent, I already know two lengths of the legs of a triangle. So I'm going to draw a little picture, and again this just helps when you're new to trigonometry to make sure that you can orient these around. But again, if I've let one of these angles be theta, then when I want to label the side lengths, tangent is opposite. Well, this is the side over here that's opposite, this one's adjacent. So when I label these, opposite is 24 given that fraction, and adjacent is 7 given the denominator of the fraction. So we already know two sides on our triangle. So when it asks me to find the cosine, remember that cosine is related to the adjacent leg over the hypotenuse. So I already know, right, cosine of theta is going to be equal to adjacent, which is 7, over the hypotenuse. Now I just don't know what the hypotenuse is yet. We know two sides of our triangle though, so we can just use the Pythagorean theorem and find that hypotenuse length. So remember, Pythagorean theorem just says we go legs squared plus legs squared is equal to, and I'm just going to put an h there to represent the hypotenuse. So when we do this, 7 squared plus 24 squared, we end up with 625 equals h squared. We square root both sides to get rid of that radical, or the squared. And we end up getting h is equal to 25. So if the hypotenuse there, right, is 25, that's the bottom of our fraction for our cosine ratio. So we just use what's given to us to represent the parts of the triangle, and we find the parts that we don't know. Okay, so I'm going to do a few examples down here again, and then I will come up and do this other example using the trigonometric identity. So let's try it right here. Determine the cosine of theta if the sine of theta is 15/17. Now again, in the end, I want to find the cosine of theta, so very similar to the last one. I'm going to put it down here. And just to remember, cosine is adjacent over hypotenuse. So when I'm done, when I write this fraction as my answer, I need the adjacent side and the hypotenuse. So I just create a little triangle. Step 1. Call one of the angles theta. Again, it doesn't matter which one. Just know if I call that one theta, then this guy's opposite, this one's adjacent, and of course this one's the hypotenuse. So it gives me that the sine of theta is 15 over 17. Now remember, sine is opposite over hypotenuse. So when I label this, opposite of theta is going to be 15, and the hypotenuse is going to be 17. So there's my two pieces. Now I'm going to go ahead and find that third side. I'm going to call it little a just because it's adjacent. So I'm going to do leg squared plus leg squared is equal to hypotenuse squared. That gives me that a squared plus 225 is equal to 289. We subtract that 225 as we solve, for a squared, and we end up with 64. We square root, a is equal to 8. So in this case, if I'm finding the cosine, adjacent is 8 over the hypotenuse, which is 17. Now, once you have all the sides of the triangle, you could find all of them, right? It gave us the sine. We could find the tangent if we wanted to, all of those. All right, let's look at one more, the number 5. So this says determine the tangent of theta given the cosine. So again, we're going to find tangent of theta. So in the end, and I'm just kind of giving us a direction of where we're headed, I need to be able to put opposite over the adjacent leg. Okay, and I'm given the cosine, and remember cosine is adjacent over hypotenuse, so refer to your SOHCAHTOA to kind of help you with that part. So we go ahead and draw a triangle, and I'm putting theta in different positions on purpose. You can choose either angle as theta. Just know that if you're consistent there, maybe it would help you, but I want you to see that it can be both spots. So if this is a over h, the adjacent to my theta there would be here, so square root of 5. And my h is going to be equal to 5, so this side's the h. So I'm going to go ahead and use the Pythagorean theorem to find the opposite leg, which I don't know. So I'm going to call that x. So let's do x squared, or leg squared, plus leg squared is equal to 5, which is the hypotenuse squared. So x squared, if you square a square root, that's just going to be plus 5, is equal to 25. Subtract the 5 over. X squared is equal to 20. Square root both sides, and x is equal to the square root of 20. Now, we want to leave these in exact radical form. We don't want fractions in our ratios at this point, so we're going to practice leaving that in radical form by simplifying the radical. This ends up being 2 square root of 5. So when I create my ratio down here, if this is 2 square root of 5, then the tangent is opposite, which is 2 square root of 5, over the adjacent, which in this case is square root of 5. Now normally I'd be done, but if you look at that, that simplifies just a little bit. I'm going to erase the O over the A. So for my final answer, I would simplify that square root of 5, and I would just end up with the ratio of 2, or 2 over 1. Okay. So practice drawing your triangle. Again, kind of walking yourself through those steps. Draw your triangle, label one of the acute angles theta. Use the ratio it gives you to label those two parts of the triangle that you already know. Go ahead and use the Pythagorean theorem to find the one leg that you don't know, and then you can make all the ratios in the world that you want out of those. And leave it in radical form if it doesn't simplify all the way down. Okay, if you're an honors student, maybe continue watching this video. I'm just going to show you really quickly how to use this identity. I don't use this very much unless it kind of works out super great. Mostly because we haven't talked about where it comes from. So you can apply it, you can use it. We'll talk more about where it comes from a little bit later. So this says find the cosine given that the sine is 4/7. If this is an equation that's true all the time, and the squared, it's really weird the way they write, I guess, these trig functions, but that just means the whole thing sine squared or cosine squared. So if we find the cosine given the sine, then essentially we would set this up where this could be substituted in for the sine. Now because it's sine squared, we could put 4/7 and we would say squared, plus we don't know the cosine of theta, so we write cosine squared theta. And again, that's always equal to 1. So that's just part of this identity that we're going to use. If I square that fraction, I get 16 over 49. Again, plus the cosine squared theta is equal to 1. And if I'm solving for theta, or sorry, the cosine of theta, because that's what I want to find in the end, then I would subtract 16 over 49 to the other side. So essentially I have cosine of theta equals 1 minus the 16 over 49 because I'm moving it over. When we subtract that fraction, cosine squared of theta is going to be equal to 33 over 49. So looking at that, if I want to undo again a squared cosine, I square root that side and I square root this side. So the cosine of theta is equal to the square root of 33, right? Remember when we do the square root of a fraction, we do the square root of the top over the square root of the bottom, and that bottom simplifies nicely. So we get square root of 33 over square root of 49, which is 7. So essentially this one would be our answer there because we solved for the cosine. Again, you can do this when using the triangle just as easy. You just go ahead and build your triangle. It gave you the sine O over H, so you would have 4 over 7. When you use the Pythagorean theorem, let's call this one x, you've got x squared plus 4 squared equals 7 squared. Essentially, you're going to get that 16 and that 49 that's subtracted in our equation earlier. You end up with that 33. So when you square root, you get x is the square root of 33. So again, if I was finding the cosine, that would be the adjacent, or square root of 33, over the hypotenuse, which is 7. So we'll get the same answer, and if you're not planning on memorizing and applying this identity quite a bit, then I would just practice with drawing the picture there.